Okay, guys, it is time for 9.5 and 9.6. It'll be in one video. It shouldn't take us too long to get through this. Unit 9 is one of those, it's just a little bit, kind of mashes everything together. So we did thermochem in Unit 6, and then the first part of Unit 9, that brings in the thermodynamics part. And then here in 9.5, they start to link thermodynamic favorability with the K value with equilibrium. And if equilibrium was not your favorite, don't panic because it's not like a lot of calculations. But if you can start to see how they can make the units connect and flow, you'll see how they'll get part A and part B and part C and part D and so on and so forth on a free response question. And then 9.6 is coupling, which in and of itself is its own little weird thing, and we'll briefly talk about that. And then in the next video, we'll be getting into 9.7, and 9.7 is electrochemistry, which is a whole new unit, but it will link back into when we learned how to do redox equations. So, and then we're done. So Unit 9 is sort of a mishmash of a whole bunch of things and puts it all together in one unit. And I think some of you are happy to be through with acids and bases because you didn't particularly care for that, which I told you guys that's a tough one. It always has been. It was always hard for me when I was first learning Chem. Okay, so let's get into it. So first things first, Gibbs free energy and equilibrium. And if I didn't mention it before, it can also just be known as free energy. That's the same thing. It's delta G, okay? And remember, we only use delta G if they're asking me if something is thermodynamically favorable or not, or if a reaction is spontaneous, sorry. I want to use delta G values if I have it. And if I have it, that's all I want to talk about. I don't want to talk about H and S and anything else. Just talk about delta G unless you don't have delta G information. And then you can talk about H and S and all the other the variables that you might have to work with. But if you have delta G or a way to calculate delta G, or if that's somehow implied in the problem, talk about this and don't talk about anything else. This is it, because you're going to take yourself off into an area where you're talking about things and you're going to probably say something wrong. So it's best to just focus on the delta G. If it is negative, it's a spontaneous reaction, and that's it. You don't need to have any other, that's a sufficient justification for spontaneity and thermodynamic favorability for the AP exam. Okay, so delta G will be negative for one direction. It's got to be positive for the reverse direction. And that should hopefully make perfect sense. It implies that only one reaction can proceed spontaneously under a given set of conditions. And so what they mean by this one reaction is they're talking about, here we go, one direction of the reaction. And you'll see in a graphic soon in just a second that it can change depending on where you are in the process of the reaction taking place, but I'll show it to you graphically and it might make more sense. However, the delta S calculations are based on 100% reactant and 100% product, or, really should say, and or. So when we calculate our delta S values, it's assuming 100%, but it's really very rarely 100% reactant or 100% product. So in reality, mixtures exist. The larger delta S values can be obtained than those that you actually calculate. So when you calculate it, it's going to calculate a little bit less than what it actually is in reality, and you know that your actual reactants and products are should calculate a little bit higher for that chemical reactions for the delta S value, because we very rarely have 100%. So just keep that in mind, that this scenario it's not perfect with the calculation, unless you just happen to have that quote-unquote perfect reaction that goes 100%, or you're at the very beginning and hasn't started, right? All right, so this is the graph I was talking about, and it looks kind of weird, but I'll read through this real quick, and then we'll talk about what the heck we're looking at. So this is a great graphic. If you can get this visually, it makes a lot of sense. So spontaneous reaction proceeds to the optimum mixture, that's going to be your equilibrium position, as it involves an even bigger decrease in delta G than going to a complete reaction, period. So stop, let's go look at the graph for a second. Then I'll come back and do this one. So they're saying that the equilibrium position gives us an even more negative delta G value than the completion reaction. So if we have reaction progress here on our x-axis, and on the y-axis, total amount of free energy of the reactants and the products, okay? That's my y-axis. So purely reactants. So this means that right here at this time 0, I have 100% reactants. And then all the way over here, these are pure products, meaning pure meaning percentage. So think of it like that. 100% product with no reactants is here. And then right here is the equilibrium mixture. So equilibrium for this particular one is lying pretty close to the products, but it's not going to be 100%. We're going to have some reactants taking place. All right, so what happens is that this, you see how it says spontaneous reaction? So if I'm here and I am swooping down this way, going from reactants towards the products, this is my equilibrium position. But it never just goes all the way down and hits equilibrium and stops. That's not how it works. It's going to go too far. It's going to overshoot it. So think about like a pendulum that's swinging back and forth and back and forth and back and forth. All right, so this it's going down, 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 and it gets to pure products right there where it's essentially all products. And then they go, whoop, nope, too much, and then it will come back. And actually what it'll end up doing is overshooting it again, and then it'll come back and overshoot it again. And you know those little things that they have those with like the balls that hang and they go click, 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 click. It's sort of like that. And it'll go back and forth and back and forth and back and forth and back and forth. So this is spontaneous. The forward reaction is spontaneous until you pass the equilibrium position. And once you pass the equilibrium position, then the reverse reaction is spontaneous. And then when you pass the equilibrium position, then the forward reaction is spontaneous. And then when you pass the equilibrium position, then the reverse reaction is spontaneous. You got it, right? Okay, I don't have to keep doing it, right? It makes sense. So that's one thing to keep in mind. The equilibrium position, so what they're saying here is the equilibrium position gives us an even bigger decrease in delta G, or a negative, a more negative value. So, because remember, delta G is going to be, you know, products minus reactions, or final minus initial. So, if I'm just looking at where the products end and where the initially started with the reactants, I have some delta G value. And it's going to be negative because it's going down in the y-axis, right? Because I started up here and it went this way. But if you notice, the equilibrium position lies a little bit lower than where the products are. So if you were to calculate the delta G from here, this delta G difference is actually more negative than this one is, which is why it's favorable. All right, so similarly, the reverse reaction does proceed spontaneously, so that's this part right here, to the equilibrium mixture, but no further, as this would then require an increase in delta G. So it's not going to want to keep going this way. It's going to hit it and then just go, it actually will go past just a little bit, but it's not going to stay. It's going to come right back. And then that's where it's going to, the rate of the forward, rate of the reverse, they're equal to each other, and then they sort of average out right over this point where it's equilibrium. But it's not going to keep going. It's going to very quickly turn around and come back. And that's how it's working. So before I talk about this slide and what's going on here, I want to click forward to the equation so you can see it. And actually, I do have it on the other page right here. So I will highlight it so you can see mathematically what we're talking about. So delta G equals negative RT natural log of K. Now that's the natural log, not the log. Please use the right key functions on your calculator when you're doing your calculation. Times the natural log of K. All right, so I'll go back. So remember that K is our concentration of our products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. Only include aqueous solutions and gases. Do not include solids and liquids, right? So that's equilibrium. That's unit 7 and 8. Now, the delta G value holds the key to the final equilibrium mixture formed. This equilibrium position is important. This delta G value determines everything. Remember I said he's the great-great-great-great-granddaddy of spontaneity. This is the boss. He is the ultimate deciding factor. He's the champion. He's the only one that we care about. All of these other things are just sort of like helpful for us to make predictions, but what he says goes. And so delta G determines everything in terms of this thermodynamic favorability for what we're doing. The more negative the delta G, that means the more positive the K value. And the further to the right, the more products that we have at equilibrium. And so let's talk about the math behind that statement and then looking at this. Okay, so, and I'm actually going to go backwards in these columns because it makes more sense in my brain that way. But so if our equilibrium mixture is mainly products, so we mostly have products, then that means my numerator is larger, which means my K value is greater than 1. So any K value greater than 1. So if my K value is greater than 1 and I take the natural log of that value, then that natural log is going to give me a number that's greater than 0. What this means is it's positive. So a number that's greater than 0 means positive, a number less than 0 means negative. So it's going to give me a positive value. Well, if I'm plugging into this equation, and I'm plugging in a value that is positive, then that's times temperature, which is going to be in Kelvin, times R, which is a constant, and Kelvin temperatures are never negative, and R is a constant. It's also a positive value. So this is a positive number, and then that's going to be multiplied by this negative number. Then that means that delta G is going to be a negative delta G. So when my K value is greater than 1, that means I have equilibrium lies towards the product side. Then that means that it's going to automatically be a negative delta G. Mathematically, it has to work out that way because there's no other way for it to work out. Now, if I have the opposite problem where I have equilibrium position is mostly reactants, that means my denominator is bigger. If my denominator is bigger, that means that this K value is less than 1. And if K is less than 1, and I take the natural log of that value, then that means that the natural log of K is going to be less than 0, which means it's negative. That's what this is telling us, that this is a negative value. So if I plug in a negative value for this natural log of K and multiply it by a positive temperature and a positive R value and then times this negative 1, when I multiply negative times a negative, that means I end up with a positive delta G. So if I have a positive delta G, then what that means is it's not a thermodynamically favorable reaction. And the last one, the scenario that doesn't happen often but can. What do we do when K equals 1? So it just happens to work out that the concentrations and or partial pressures or whatever we got going on all come up to where my numerator and my denominator are the same number. So the K value is 1. So if my K value equals 1, when I take the natural log of 1, I get 0. So in this particular case, that means that the delta G value would be equal to 0, because if the natural log of K is 0, it's times T times R times the negative 1, which is irrelevant. The fact that there's a negative 1 out there, delta G is just 0. Okay. So that's really important that you kind of just sort of get your brain wrapped around that. And just keep in mind that the things that are favorable, the things that are considered favorable are a negative delta G, and I'm going to put a big star, or several, because he's the boss, right? A negative delta G, a K value that is greater than 1, okay, K value that's greater than 1, a delta H that is negative. I should just put a negative in front of it. A delta S that is positive. And we're going to add another one to this list once we get through 9.7, okay? It's going to be the cell potential, which is coming up soon. Okay. So these are all we can predict. This tells us pretty more definitively how so, because it plugs right into this equation. So delta G and K are very closely linked together. Now, I'll walk you through the algebra to solve for K, because they do sometimes like to ask you to do this, and the equation's also here. They're not going to give you the equation for K on the formula sheet, but they will give you the equation for delta G. We do call this the rat link equation because no reason other than if you just sound it out, that's what it looks like. But let's just go through the algebra, because you may have to do this on the test, and there's absolutely silliness in my brain for you to miss points on something as simple as just algebra. Okay, so what we're going to do is, let's say you have the delta G value and you need to solve for K. Like, this is what you're solving for. Then, as always in algebra, I need to isolate K, right? I need to get it by itself. So if I divide both sides by negative RT, that goes away. And I have the natural log of K equals this delta G for the reaction over negative RT, and this negative can be pulled out into the front. This is fine. Doesn't matter. And then that's good. I'm almost there, but I haven't completely gotten just K. I have the natural log of K. So again, you don't have to have this memorized. It's on your calculator. Remember, the inverse of the log is 10 to the x. Your calculator tells you what your reciprocals and inverses are, just like the inverse of the square power is the square root. So the inverse of the natural log is e to the x. And algebra's law states that what I do to one side of my equation, I have to do to the other side of the equation. So I need to raise both of these sides e to the x, e to the x. And so what happens is e to the x and natural log cancel because they're inverses. So then I just have K equals e, and x is everything here. So it's his exponent becomes negative, whatever the delta G value is, over r times t. So that's where this is coming from. Okay, so that's where that equation is coming from here, and also on the slide, on the PowerPoint. So be able to do the algebra to work through that. Now, the R values on your formula sheet, you have more than one R value. So that's another thing I want to talk about. Pay attention to your R values, because there are a couple on there. So you have the R value that's like 0.0821, and it might say 8206, whichever, it doesn't matter. This is our gas laws R. Okay, that's gas laws R. How do I know that's gas laws R? That comes from PV equals nRT, right? And so look at your units. The unit should be ATM times liters over moles times Kelvin. Look at the units. Atmospheres, pressure, gas laws, okay, pressure, volume, temperature, gas laws. Okay, and then this one is 8.314 joules per mole times Kelvin. So this is energy R. Why is he called energy R? Because he's joules. Okay, energy R is joules. So when you're in thermo, you're going to use the energy R, because that's the one that makes sense, because we're talking about kilojoules of energy. And so make sure you're using the right units, and then also keep up with your conversions, okay? That's going to be important. So 8.31 is your R. T's got to be in Kelvin, so that's just like gas laws, so keep that consistent. Add 273 to your Celsius. The delta G, when you do this calculation, is going to end up giving you joules per mole, and it is okay if you leave it in joules per mole unless they tell you to give the answer the appropriate way, which would be kilojoules per mole. If you go ahead and convert it, that's fine, but don't do it if they don't ask you, because you get no extra credit for being oh so smart and knowing that you technically would convert it to kilojoules. They don't care. And what you do is, number one, you waste your time, and number two, you run the risk of making an error over something simple that if you had just left it alone, you wouldn't have lost points on. So leave it alone unless they specifically say give it in kilojoules per mole. Or you have to take it somewhere else later and use it, and you need to convert it. They will give you a point if they don't indicate what unit to use. they'll give you points regardless of whether you do it in joules per mole or kilojoules per mole under this calculation. But pay attention, because if they specifically ask for one or the other, then they're not going to give you credit if you use the wrong unit, even if it's numerically correct. All right, and so as delta G becomes more negative, so that means more negative. So what's more negative? Negative 30 is more negative than negative 2, right? It's more negative. So if you think about a number line here, more negative is further to the left on the number line. So as delta G becomes more negative, K is going to be a larger value. So the larger the K value, which means the more on the side of the products you are, the more negative, that means the more spontaneous your reaction is, more favorable you will have. And then the opposite is true. As delta G becomes larger or more positive, so that means as the number is approaching 0, and possibly crossing over to become a positive value, then the K value is going to decrease. Okay, so delta G and delta K, I'm sorry, that's not delta K. If delta G and K are inversely proportional to each other, so as one goes down, the other goes up, and so on and so forth. Why? It's different than normal because it's the natural log. Because normally if we saw things on opposite sides of the equation, we would say they are directly proportional. But it's because we're taking the natural log of that value, they're inversely proportional. Okay, so what does thermodynamics tell us, and what does it not tell us? So thermodynamics provides us with some powerful tools when considering chemical reactions. So it can predict whether a reaction is feasible or not. Is it going to happen? Possibly, yes, no, maybe. What are we looking at? Thermodynamics can predict the conditions necessary for a reaction to take place, and it can predict the position of the equilibrium. So that's what it can do for us. Now, where are we limited thermodynamically is a couple of things. But the issues with the thermodynamics that doesn't give us the total picture is the fact that it only looks at the reactants and the products. It doesn't look at everything that's happening in between. So, I already wrote on that paper. Let's get this one. So think about this energy diagram, right? It only looks here and here, but it's totally leaving all of this part out. And this part also matters, right? So it's also relevant. So it doesn't take a look at what's happening in between, like what are the pathways? What's the activated complex? What's the activation energy? Are there catalysts involved? What are they doing? So it cannot predict how fast a reaction is going to take place, so it's got nothing to do with kinetics, and it doesn't give us anything to do with the mechanisms and the steps going through getting from the reactants to the products. Okay, so we have a problem to solve really quickly. Given the equilibrium constant at 298 Kelvin for the following exothermic reaction, calculate the delta G for this reaction, and they give us the K value as well. So let me get this out of the way. Okay, well, for this one it should be just plug and chug, right? So I'm looking at, pay attention to your problem. They asked me to calculate the delta G. So I want to solve for this. There's so many ways to get delta G. So I've got to look at what did they give me. They gave me temperature, which is 298 Kelvin, and they gave me a K value, which is 1.4 times 10 to the 6. So if the minute I see a K value related to delta G, then I know I'm doing the Ratlink equation. So let's plug in and solve. So delta G equals negative, what is R? It's 8.31, and your units for R are joules per mole times Kelvin. And the temperature is 298 Kelvin. And I have the natural log of 1.40 times 10 to the 6, and that's a pretty big K value. Because 10 to the 6, that's not a negative 6. So my prediction is that this is going to be a very negative value. Okay? So delta G equals Well, first thing I'm going to do in my calculator is go and take that negative log of this number here. I'm sorry, not the negative log. My brain's still on acids and bases. I'm taking the pH. No, the natural log of 1.4 times 10 to the 6. Okay. And I'm going to multiply that by 298. And multiply that by 8.31. Ooh, that is a ginormous number. Okay. So 35,045. So this is what it says. 0.7. And I'll deal with sig figs in a second. All right, my K's cancel out. And so I'm left with joules per mole. Okay, going back to my problem, I have 3 sig figs in my answer. So I have a couple of ways I can solve this or write this answer out, but the best way is going to be scientific notation. Technically, there should be this. So it's going to be 3.50 times 10 to the, move the decimal place, 1, 2, 3, 4. 10 to the 4th joules per mole. They did not ask me for kilojoules per mole. I am not going to waste my time, number 1, converting it, and number 2, running the risk of making an error. Leave it alone. I'm done. It's good. I don't have to do anything else. So that's my answer. Okay. Now, coupled reactions. So coupled reactions, coupled is exactly what it sounds like. Okay, it's a couple. You're putting things together. And so a coupled reaction, which is 9.6, is when we are coupling reactions together. We're sticking them together. It's like they're now a couple. They're getting married, or they're boyfriend, girlfriend, or whatever you want to call it. They're significant others to one another, whatever. So in this reaction, or these reactions, we mix them together. We've talked 5 million times. If you guys think back to first year chem, when I had you guys and we would talk about water and how water is H2O, and we would talk about going from an ice cube to liquid water to a gas. And I would say, is it still H2O? Is it still water? Is it still water when it goes from a solid to a liquid and a liquid to a gas, or did we split the water molecule when we did that? And then we all started to finally understand that we weren't splitting anything, that it was just H2O. Because it takes a lot of energy in order to split water apart into its elements, which are hydrogen gas and oxygen gas. So one way I can split water is by zapping it with electricity. So this is a battery, and I have electricity flowing into this water, and it's splitting the water molecules. So if delta G is positive for one direction, it will not proceed spontaneously under that condition. So this condition here, this is going to be individually a positive delta G, because it does not just become hydrogen gas and oxygen gas. I have to do something to it to make it happen. I got to zap it with electricity. Okay? So however, when I do apply some external source of energy, then I can put in enough energy to overcome that Gibbs free energy, that delta G value, so I can then push that reaction forward. So what's happening is the water can use the energy that's in this battery to overcome the delta G energy. All right? So it can cause water to decompose into its elements, but only with the use of electricity. It takes a good amount of energy, actually, for water to do that. So we have non-favorable reactions. That means positive delta G values. How do we overcome them? Well, here's an example. So I have this copper sulfide. So this is going to be copper sulfide breaking down into copper and sulfur, and so it's decomposing into its elements. It is not spontaneous. It's a positive delta G value, and that should say per mole, but this is an older slide, so it just says kilojoules, but don't do that anymore. It's got to have per mole on there. So because delta G is positive, we will not be able to separate out the copper. So let's say you have this copper sulfide. We want it to decompose because we want the copper for something. I don't know. We're going to go take it and do something with it. So I have to figure out a way that I can react or put this copper sulfide with something else in order for this reaction to proceed, even though it has a positive delta G value. So I need to couple it with another reaction. Well, if I couple it with this, which is the synthesis reaction of sulfur and oxygen to create this sulfur dioxide, this is a spontaneous reaction, big time. And look at this. This is a pretty big delta G value. I mean, it's big in the negative sense. So it's negative 300.4 kilojoules. So that's a pretty negative value. So we can mix them together, and what happens is the sulfur will react with oxygen, and when it reacts with oxygen, it creates the sulfur dioxide. And as that happens, I need more sulfur. And as the sulfur is reacting from this equation up here, because the sulfur comes from here, as this sulfur is separating from this copper sulfide, and I'm getting just the sulfur, I'm having copper that's left behind, which is my whole goal, is to just get this copper left behind. So if I have this copper sulfide, it's not going to just do this on its own. I have to mix it with something else. What do I mix it with? I'm going to mix it in with some oxygen, because when that happens, the sulfur that I do get decomposed over here will react with oxygen and create the sulfur dioxide, so this copper 2 sulfide will just leave behind the copper. So by coupling these two chemical reactions together, we're able to extract much of the copper metal via a spontaneous reaction. How is it spontaneous? Because if I have these two reactions that each have their own delta G values, if I mix them together, if I add the two equations together, then what happens is I just add their delta G values together. So positive 86.2 and a negative 300.4 sum up to give me a negative 214.2 kilojoules per mole. And so that makes this a spontaneous reaction. This by itself, not spontaneous. This is. And summing these two equations is simple enough, just like when we did mechanisms. In this case, you would just cancel out the sulfurs because they're on opposite sides of the equation, and then you sum them up. That's coupling. That's all you have to do. There's a little more to it than that, obviously, but AP doesn't get super heavy into coupling, but just so you know. All right, so we have this equation or example in our notes, but I'll just do it right here. So it says write the overall reaction and determine if this would be a good example of a coupled reaction, and would the overall reaction be spontaneous? Well, let's take a look. ZnS gives me Zn plus sulfur, and the delta G value is 198.3 kilojoules per mole. Not spontaneous because it's positive. That's a pretty big positive value. And then if I take the sulfur and I mix it with oxygen, I will get that sulfur dioxide, and that's a negative 300.1 kilojoules per mole. So spontaneous, this will happen. The only thing is it just needs a little bit of sulfur to make it happen. And if it gets it, then it'll react with the oxygen and give us sulfur dioxide. And then if this is pulled away to come down here and react with the oxygen, then more of the zinc sulfide is going to decompose. So is this a good example of a coupled reaction? And the answer is yes, it's a good example of a coupled reaction, because this one's not going to happen all by himself. When I sum these up, let's get the exact number. It's going to be around 100, but let's see. I have a 198.3 minus 300.1, so 101, negative 101.8. So it's negative 101.8 kilojoules per mole. Sulfurs cancel, so I have zinc sulfide plus oxygen gives me zinc plus sulfur dioxide. And it is this reaction is spontaneous. So this is a perfect example of a coupled reaction, because you have one that is equation number 1, which is not spontaneous on its own. When I mix it with this other reaction that is spontaneous, I end up with an equation that is thermodynamically favored, therefore a spontaneous reaction. So yes, this is a perfect example of a coupled reaction for the reasons I just stated, and that's the overall delta G value, and that's it. Simple enough. All right, guys. Talk to you later. Bye.